The story of the existence of the universe 13 billion years ago, that moment when we think everything began. Existence born from nothingness, the first steps of the universe. So how did this happen? Perhaps this is the most important question for all humanity, for science and knowledge to be answered, for which many possibilities are researched. We know that theories, experiments conducted, physics and philosophy transcend boundaries. Everything we know, we think, is based on all processes and causality. We are trying to find and understand the answer to the question of why everything that happened in the creation process of the universe was so. But at the very foundation of the process, we are questioning how or why all the universe that formed or was created exists. We certainly do not know the exact answer yet. We know that this desire to reach these answers is not only due to a lack of curiosity. This is an existential issue. Why and how do we exist? Perhaps as said by Stephen Hawking, one of the most important cosmologists of the last century who had many researches on this subject, there was no before creation. If we think of space and time as an inseparable part of the universe we live in, we can say that time also started simultaneously with the beginning of the universe. We understand that there was no space before time. Both existed at the same time. And of course our universe formed along with this. Let's come to Hawking's examinations of space-time. While analyzing the geometry of space and time in the past, he observed that it narrows, curves, and finally closes completely. But the pleasure of searching beyond this, like searching for new things north of the North Pole of the Earth, would not give us a result and meaning. Perhaps a beginning, as we suppose never actually happened, only our power to observe the universe was limited. Scientists believe that what enabled the Big Bang to occur and provided suitable conditions for life after this explosion is the moment when a complete expansion, which we call inflation, occurred. This inflation experienced in the formation of the universe happened and ended in a very small fraction of a second. And according to some physicists who speculate on this, they claim that this was not the only inflation episode that occurred in the cosmos. On the contrary, perhaps inflation continues forever elsewhere in the cosmos. In a strong and infinite multiverse, it might be producing new universes. Perhaps our universe is the newest produced version of an infinite cosmos series, as thought in the Big Bounce theory, which is another possibility, continuously expanding and contracting within itself. Instead of the universe starting from nothingness and expanding exponentially to exist, scientists like Paul Steinhardt say that everything within the universe experiences systematic growth and shrinkage. Perhaps we are not developed enough to solve this mystery. Our scale understanding is not perfect enough. Physicist Roger Penrose, according to his idea, stated that shapes could form with properties independent of their dimensions. Perhaps the same was valid for the cosmos. According to physicist Roger Penrose's idea, for the universe not to lose its sense of time and scale, it must not be infinitely large and infinitely small. If this is God's chess, the rules do not change whether chess is played on a small board or on a chessboard the size of a stadium. Perhaps our cosmos came into existence as a result of many dimensions colliding with each other. Along with this thought, we need to examine superstring theory. According to superstring theory, the basis of reality is actually assumed as small strings vibrating in these 11 dimensions in hyperspace, assumed to be 11-dimensional. We know that the universe we currently live in is 3-dimensional, and there is one time dimension. It is a single brain in the bulk of this vast universe. The expansion of our universe over time, along with its beginning, perhaps occurred with the collision of brains in a dimension higher than the dimension we feel. Where is the hottest point of the universe? Perhaps something else we do not know. Perhaps the answer to this existence lies in a corner of mathematics or physics science that we have not yet solved, not yet discovered. We have not yet solved the mystery in the creation of our universe, and with the emergence of many theories, it still stands as a story. Nevertheless, what we are sure of is that our universe really began 3 billion years ago. What we are really curious about is the story after that. Where is the hottest point of the universe? Imagine the natural fusion reactor found in the core of a star. Even if you fell there and thought you would turn to ash, you would have struggled in vain. Because we need to know that the temperature in the core is only 15 million degrees Celsius. Perhaps if we turn our eyes to supernovae, where more violent events occur. During a star's ordinary but dramatic demise, very heated gas pieces shoot out in all directions, and this creates a gravitationally compressed neutron star at its center. This place creates even more heat than stellar furnaces. It reaches almost 100 billion degrees Celsius. But you are still wrong. The hottest place is not here either. On our Earth, the highest temperature recorded so far was located 100 meters below the ground with a pile of snow on it, on the shores of Lake Geneva in Switzerland. Of course, finding and solving this mysterious place did not happen as a result of a natural process. It was discovered as a result of research done by spending billions of euros of huge budgets. The Large Hadron Collider that took place at CERN in 2012. By colliding two atoms, it managed to produce a massive temperature of approximately 5.5 trillion degrees Celsius. Can you imagine this? The temperature released as a result of this collision is 50 times hotter than a supernova. But even this achieved temperature is not the maximum temperature we can reach. The definition of temperature is the reflection of the energy created by any particle, the motion it emits. The lowest temperature limit at which particles form is absolute zero, minus 273.15 degrees Celsius. This is theoretically the lowest limit. So what is the upper limit? It is the particle's own energy. To explain further, it is the temperature of the energy it emits before disintegrating. The science world calls this Planck temperature. Its describable measure is approximately 1.4 times 10 to the power of 32 Kelvin, that is, 32 more zeros next to 1.4. This name comes from the famous theoretical physicist Max Planck, born in Germany, one of the masters of quantum physics who lived in the 20th century. With this theory, Planck brought together his own discovery, the Planck constant, the gravitational constant, and the speed of light, and discovered and defined the smallest unit of measurement in the universe. If we examine this definition, a Planck length, 100 quintillion times smaller than a proton. If we look at Planck time, the time it takes for light to travel that distance, and we see Planck temperature. Of course, these are numbers that the human brain struggles to comprehend. We are creatures designed as medium-scale evolved beings with certain limits. But the truth is that these units gain meaning together with the universe. Because we do not live in a static universe, it continuously expands. The universe's expansion faster than the speed of light is thought-provoking. Is the universe infinite? We do not know this yet. Let's say it is infinite, then infinity always prevailed. Perhaps it was created large and infinite from the beginning. It did not expand from a single point and later. Of course, when we examine the universe we observe, we see some differences. It tells us that there are some limits. For example, the distance light can travel is the only part we have the chance to examine and observe, that we are in interaction with. When we assume that it is possible to go back in time, the observable part of the observable universe shrinks, until our universe that we can observe is compressed into a point with a diameter of only 1 Planck length, 1 Planck time old. At this very moment, the temperature of the entire universe was exactly at Planck temperatures. This experienced moment, only 10 to the power of negative 43 seconds after the beginning of space-time, is called the Planck epoch. And this was a very strange and also weird place. Right now, everything is governed by 4 fundamental forces known scientifically. The strong nuclear force that keeps atomic nuclei together, the weak nuclear force that governs and controls radioactivities, the electromagnetic force that directs energy and gravity. The first 3 forces can be quantized, meaning they are carried by messenger particles, gluon, W/Z bosons, photon. But gravity is different. According to the famous scientist Einstein's general relativity theory gifted to humanity, he defined gravity as a curvature, a bending in the fabric of space-time. The real problem is perhaps here. During the Planck epoch period, our entire observable universe was squeezed into an area trillions of times narrower than a proton. The rules at such a small scale describe the whole of quantum mechanics. In quantum physics, nothing is definite. There is nothing that is absolutely certain. These can be explained with probabilities and uncertainties. Let's come to the whole of contradictions. We see that the concept of general relativity, large scale and gravity, and quantum mechanics, small scale, are incompatible with each other. In the Planck epoch, however, both had to be equally valid. So how? The name of the theory we are trying to find the answer to this question is called quantum gravity. Then let's examine a few crazy ideas related to this subject. Graviton. Gravity being carried by a messenger particle, graviton, like other forces, but due to gravity's weakness. It makes detecting the graviton impossible. Quantum gravity loop. This view is the thinking that space-time is not on small scales, but consists of pixelated energy loops. String theory. The idea that fundamental particles in the universe are not composed of points, but are one-dimensional strings vibrating with each other. The vibration of strings with each other, the shape it creates determines both forces and matter. But there is a truth that its mathematics requires 11 dimensions for it to work correctly at this point. In 1950, physicist John Wheeler made a definition, also taking time into account to explain this complexity, quantum foam. He explained that space and time are not smooth and do not exhibit continuity thanks to the uncertainty principle at the Planck scale. It was as if it was a boiling and foaming fabric with a dynamic structure. Wormholes and micro-black holes formed spontaneously and then disappeared. In a quite compact universe with a high-energy field, even for the shortest instant, it made everything possible. What ended the unpredictable chaos in the Planck epoch and started a new era was the universe growing and cooling in a period like 10 to the power of negative 35 seconds. We said that everything in the universe is explained and governed by 4 fundamental forces. The gravity force that allows you to sit comfortably on your chairs right now. Like infrared light, electromagnetism, emitted from a remote control, the self-force that keeps atoms close to each other, and the weak force that enables the radioactive spread of potassium in our body. But in the first moments of time, all conditions proceeded differently. The identities of these forces begin to melt at high-scale energy. Let's assume this as flipping a coin. While the coin is in the air, we cannot know whether it is heads or tails. There is only a coin spinning in the air. When the coin stops and loses its energy, then 2 options are determined. At the beginning of the universe, at high energies, forces were seen in this way. At the beginning, the electromagnetic force and the weak force combined to form the electroweak force. In the grand unification epoch following the Planck epoch, that is, at even higher temperatures, the electroweak force combined with the nuclear force to form the electrostrong force, also known as the unified force. In the formation epoch of the universe, the tiny cosmos was covered with particles that appeared to be in an intense identity crisis. Photons were naturally transforming into matter and antimatter pairs, quarks, leptons. Afterwards, these particles were turning into photons. Messenger bosons were actively transforming quarks into leptons, and leptons into quarks. This picture we saw was literally a dance that energy and matter performed spontaneously in the cosmos. With 10 to the power of negative 36 seconds after the beginning of the universe cooling down and its formation starting, allowing strong forces to emerge, 3 forces had now emerged: strong, electroweak, and gravity. But in this apparent picture, a big problem was visible. Although these theories explain the first moments, they remain insufficient and inadequate to explain the universe we actually observe and the entire universe. 2 great mysteries appeared. Horizon problem. The average temperature from end to end of the universe is mysteriously equal to each other. If the universe is thought to be 14 billion years old, it seems impossible for enough time to have passed for light to travel from one end of the universe to the other. So how did they homogenize so much? Flatness problem. We can detect that on large scales the universe appears flat. This is an incredible symmetry and tuning. For example, it is like a tuning where when we toss a flat coin into the air, it falls perpendicular to the ground in perfect proportion. Yes, one more mystery. So where are the magnetic monopoles? Yes, we have them in our universe, proton/electron. But why have isolated magnetic poles, only north or only south, never been observed? In 1979, physicist Alan Guth put forward an idea that brought a solution to these 3 mysteries: cosmic inflation. Guth's theory was the idea that after the Big Bang occurred, between the first 10 to the power of negative 36 and 10 to the power of negative 32 seconds, the universe expanded very rapidly, exponentially. To explain the theory further, it was that the universe increased its size by at least 10 to the power of 26, that is 100 billion times billion, times in a period shorter than a trillionth of a second. So how did this inflation solve these problems? Horizon problem. Before inflation, our observable universe, which had its thermal structure and balance, consisted of a very, very small piece. Therefore, every part of it had formed at the same temperature. Flatness problem. If we explain this with an example, think of a balloon. If you inflate a tiny spot on it, you see that spot flatten. Our universe inflated like that. Monopoles, even if we assume they existed. Inflation dispersed the poles so far that it made observing them in our observable universe difficult. Perhaps only one exists. Finding it is almost as difficult as finding a needle in a haystack. So how did the biggest mystery, the Big Bang, occur? We can explain this most clearly as follows. When inflation ended, it poured all its energy into matter and reheating occurred, and thus the Big Bang process began. In this process, the temperature was almost quadrillions of degrees, and along with this, the electroweak epoch began. Symmetry breaking and the birth of mass symmetry is the truth of the universe, and we see it everywhere in nature. Humans created with symmetrical bodies. Starfish created with 5 arms. When we examine this scientifically, symmetry is some properties remaining the same even if something changes according to the nature of creation. Physical laws are also symmetric. But when we examine our universe, we do not encounter a perfect symmetry. Let's give an example, like our heart not being in the center of our body, but shifted to one side. We see that there are imperfections in our universe as well. For example, like matter being much more than antimatter. When we look at the first moments, we see that everything was symmetric. But with the drop in temperature, rapid phase transitions occurred, just like water suddenly turning into ice. When we examine one of the important-looking phase transitions, we detect that it occurred approximately 1/1,000,000th of a second after the Big Bang. This is the separation of the electroweak force. This separation caused the perfect symmetry of the universe to be broken, and afterwards, a new field emerged in the fabric of the universe. This was named the Higgs field. To understand the Higgs field better, there is a famous definition and analogy. Think that you are at a crowded cocktail party. If an ordinary person enters the hall, they progress easily without problems. But if a famous scientist enters the hall, other guests who see him want to chat with him, and his progress stops. In the example, that crowd and the condition it creates is the Higgs field. The famous person is a particle that has gained mass. The gossip wave circulating in the crowd is the messenger Higgs boson. This field and particle discovered by Peter Higgs in the 1960s, when we come to today, was detected in 2012 at the Large Hadron Collider at CERN. The Higgs field, which leaves photons massless, is observed to give large mass to W and Z bosons. At the same time, it also provides certain amounts of mass to quarks and leptons. The birth of mass occurred in this way. 1 second after the Big Bang occurred, the quark epoch came to life. Our universe was now filled with all known fundamental particles, quarks, leptons, gluons, and 4 separate forces. But there was still chaos. It was hot and chaotic. The fine-tuning in the formation of the universe, the physical constants occurring in our universe, such as the speed of light, gravitational constant, fine structure constant, may seem random at first glance, but it appears that they are not. They are incredibly fine-tuned like a work of art. For example, the fine structure constant is 1/137. For instance, if it were slightly larger or smaller, we would see instabilities and atoms would behave unstably, and along with this, the chemistry of life would not form. If we give another example, let's think that gravity was a little stronger. This would mean the universe collapsing quickly, or let's assume it was weaker, then the formation of stars and galaxies would not be possible. So the real question is, did the universe form by chance? Or are we in only one of countless possible universes that have such established balance, that have such correct values? Actually, this is seen as one of the most fundamental supports of the multiverse theory. Protons, neutrons, and the antimatter mystery about 1/1,000,000th of a second after the Big Bang occurred, the temperature experienced a drop like 1 trillion degrees. This drop allowed quarks to finally bind into protons and neutrons. Again, we see a fine-tuning here. We observe that the down quark is heavier than the up quark. This seemingly small difference causes a neutron to be almost slightly heavier than a proton. With the cooling of the universe, with the help of weak forces, it enabled protons and neutrons to transform into each other. With the drop in energy, transformation into the lighter proton was provided. With this event, upon freezing, in our universe, for each neutron, there were approximately 7 protons. This mentioned ratio is vital for our universe. What if there were more neutrons? Well, then everything would turn into helium gas, and an unreactive universe would exist. We need to know that protons are the basis of chemistry and life. Another great mystery. The question, where is antimatter? According to scientists' theory, matter and antimatter should have been created in equal amounts. Because when matter and antimatter come together, they annihilate each other and thus turn into energy. But today, in the universe, there is not much more antimatter than matter. But we know that almost everything is made of matter. So how did this happen? The answer to this may lie in a phenomenon thought to be CP violation, along with the symmetric breaking created by weak forces. The very slightly different behavioral approach to matter and antimatter may be the cause of this. Perhaps undiscovered. Unstable particles, for example right-handed neutrinos, may be acting in favor of matter. This may be one of the open and important unresolved mysteries in physics. The Dark Ages and the first atomic nuclei, what happened 1 second after the Big Bang occurred. With the cooling of the universe, it had become suitable for the emergence of atomic nuclei existence. But before, there was an obstacle. This obstacle was the deuterium bottleneck consisting of proton and neutron. High-energy photons were breaking deuteriums. Let's look about 3 minutes later. The universe's temperature dropped to levels where deuterium could remain safe. And afterwards, a sudden and rapid fusion explosion occurred. Deuterium plus proton equals helium, 3 helium, 3 plus neutron equals helium. For now, let's look at the elements in this formula. Helium, 4, is goal-oriented and incredibly stable. Almost all protons freely roaming in the baby universe turned into helium in this experience process. All calculations say that at least 25% of the mass formation rate of the universe must have started with helium. Today's data indeed gives the information that in this process, there is 23 to 25% helium in the universe. This experience Big Bang is in the nature of strongly proving the scientists' theory named nucleosynthesis. The quite furious-looking fusion ended when the universe was only 20 minutes old, and only hydrogen, helium, and trace amounts of lithium remained. But still, the universe was still very hot, literally resembling an ionized, charged plasma. Electrons were having the problem of not being able to bind to atomic nuclei. There was no light in the universe. It was opaque. The universe was literally living through dark ages. This situation continued for almost 380,000 years. The emergence of first light and cosmic microwave background radiation. Let's come to what happened 380,000 years after the Big Bang. Let's get into some technical topics. Our universe cooled to almost 3,000 Kelvin. With the possibilities provided by this cooling, it created sufficient conditions for electrons to be captured by atomic nuclei to form neutral atoms, primarily hydrogen and helium. This moment and process experienced in science has been given the name recombination. Actually, this event experienced was a revolution. The transformation of nucleus-charged particles, ions, into neutral atoms prevented photons from being constantly scattered around. Of course, this event allowed light to travel freely for the first time. The first light that emerged is still alive and still with us around us today. Of course, with the expansion of the universe, that light lost its energy and its wavelength lengthened. Perhaps the light's energy decreased. It does not appear as on the first day, but filling the universe by serving as a microwave. In science, this is called cosmic microwave background radiation, CMB. In 1965, physicists Arno Penzias and Robert Wilson accidentally discovered this noise, CMB, and this won them the Nobel Prize. CMB was in the nature of evidence proving the Big Bang. But much more importantly, the tiny temperature fluctuations on it show why density in the baby universe created differences. Thanks to the force of gravity, these fluctuations grew, causing the seeds of the galaxies and galaxy clusters we see today to be sown. CMB also carries traces of all sound waves in the universe. The pressure of photons caused matter wanting to cluster with gravity to be pushed. If we explain this event with an example, it literally created baryonic acoustic oscillations like ripples in a pool. These oscillations that emerged froze when atoms scattered around and photons escaped. In today's galaxy atmosphere, we can still see traces of these frozen fluctuations at intervals of approximately 500 million light-years. This provides cosmologists to analyze and measure the expansion of our universe, literally serving as a standard ruler. Dark matter and the invisible skeleton CMB theory and analysis and observations made in our galaxy revealed that matter and atoms were only a small part in this story. The speed of galaxies' movements and rotations was at a rate too high to be explained by the mass of stars and gas we can observe. The observed matter and galaxy clusters were moving too fast to be possible to stand side by side and together. I want to share an important footnote with you. There is a type of matter that does not cool and does not emit any light, interacting with gravity, covering almost a large part of the universe we can define as 85%. Dark matter. So let's examine dark matter in more detail. MACHOs, massive compact halo objects, could be objects composed of normal matter resembling brown dwarfs, black holes that swallow even indefinite light, faint neutron stars. But observations show they are not in very large numbers. WIMPs, weakly interacting massive particles, the currently most probable popular candidate. Perhaps particles that have interacted with weak force and gravity, outside the standard model. CERN is working on and wants to find this most important mystery. And also quite advanced underground detectors are searching, but no finding has been encountered yet. Another predicted property of dark matter was that it started clumping earlier than normal matter, even in the Dark Ages. It literally formed an invisible skeleton. Normal matter containing hydrogen. Helium gas was later lost in the deep wells of this dark matter. This event created the necessary conditions for the formation of the first stars and galaxies. There is a truth that if dark matter did not exist, galaxies could never have formed. The first stars and the beginning of chemistry, hydrogen and helium clouds, thanks to dark matter, remained compressed enough. Approximately 100 to 200 million years later, the first stars, namely population 3 stars, shown. Massive, sized stars composed of pure hydrogen and helium, for the first time produced heavy elements, namely carbon, oxygen, iron in nuclear temperature furnaces. When their deaths occurred, they scattered their elements into space. Thus, new stars were born and enabled planets to form from gas clouds. And the beginning of chemistry occurred. Even in space and interstellar clouds, it was discovered that complex organic molecules, namely the building blocks of DNA, could form. And the materials of life in the universe were scattered everywhere in the universe. Dark energy. The mysterious propulsive force. We have come to the final act of the story. Even greater mysteries confront us. In 1998, while analyzing distant supernovas, a shocking discovery occurred. It was observed that the expansion of the universe was not slowing down. On the contrary, it was accelerating. This is completely opposite to the thought that gravity was expected to hold everything together, as thought. So what was the reason for this? It was suggested that a new component that became quite dominant about 5 to 6 billion years ago existed. Dark energy, according to examinations made. It is assumed to constitute almost 68% of the energy density found in the universe. Perhaps dark energy could be an energy in an intrinsic cycle belonging to empty space. Einstein's cosmological constant in his theory. Or it could be a dynamic structure or field called quintessence that changes over time. We do not know exactly what it is. But the effect it creates is quite clear. The universe is expanding increasingly faster. This indicates that over time, galaxies will move away from each other and disappear from sight, a cold and dark and lightless universe. Conclusion. The fine-tuning of creation and we, beings living in the universe, and we have come to the conclusion part. After a very long journey for us of an estimated 13.8 billion years, we are a grain of dust in the universe. Everything operated according to the set of rules determined at the beginning of that first second in the creation of the universe. The 4 forces we mentioned, the properties of matter and physical constants, all are so finely planned and adjusted that the slightest deviation would make stars, planets, and life impossible. So is this really a coincidence? Or a design woven with divine fine adjustments? Or do we exist in a rare one of countless possible universes where life found life? The answer to these questions we know as far as philosophy and science intersect. But there is a truth. As conscious beings, we are beings made of stardust. Trying to understand this universe with limited knowledge in the evolutionary process. And the discovery still continues.